You may recall that angles like 50 degrees and 410 degrees are called coterminal angles because they end in the same location. If I were to take 410 and subtract 360 from that, I'd end up with 50, meaning those angles would look identical. Now, because those angles look the same, it means the sine of those two angles, or the cosine of those two angles, would be the same. We call trigonometric functions periodic because these values repeat over and over and over again. It turns out, and we're going to talk much more about this later when we start graphing, but it turns out for now, for what we're going to need, sine and cosine both have a period of 360 degrees, a full circle, or 2 pi. The tangent graph, as well as its reciprocal, actually has a shorter period. The period is half of that, meaning the tangent graph, or the tangent ratios, repeat every 180 degrees, or 1 pi, half a revolution. So let's take a look at how we can use this property to our advantage to help evaluate some trigonometric expressions. So what I'm going to show you is just an option for how to do these problems. We've already done a problem where we've found the sine of 765. It was our 3-step problem, sketch it and find the reference angle and all that. We can certainly still do these the same way, but let me show you how we can use coterminal angles and the period of these functions to make the angles a little more convenient to use. I'm dealing first with a sine graph, or a sine function. The period of that sine graph was 360 degrees. So I'm going to go ahead and subtract 360 from the angle I'm given, and I'm going to see that I get, well, of course, a smaller angle. It's still not quite as small as I want it to be, though, so remember, we could add or subtract 360 as many times as we want to, and it turns out that if I subtract 360 twice, I end up with a new expression that's just sine of 45 degrees. Well, the sine of 45 degrees should be the exact same thing as the sine of 765, because we just found out that those are coterminal angles. Well, the reason that this can help me then is because sine of 45 is just in the chart that we've made. So I can just look up the sine of 45 and see that the answer to this is the square root of 2 over 2. So I can use those periodic properties to make this problem somewhat shorter and somewhat easier to do. Sometimes this is a shortcut, though. Let me show you this next example where it turns out it's not a great shortcut, but we can still use this. So I'm dealing with the secant of negative 240 degrees. Well, the period of a secant function is also 360. So this time I'll want to add 360 to try to get my angle to be a little more convenient. When I do that, I end up with the secant. And remember, you can add or subtract 360 as many times as you want to. When I add it just once, though, I end up with the secant of 120 degrees. Now, unfortunately, 120 degrees is not in the chart that we made, so I'm still going to have to do this as a 3-step problem. So you'll see what I mean. Like, this isn't necessarily a shortcut for this problem. It's still going to take us a little bit of work, but I don't have maybe as nasty of an angle to use, I guess. 120 degrees is going to be over here in quadrant 2, so this was step 1 of our 3-step problem. Sketch it and find the reference angle. That reference angle is going to be 60 degrees, because that's what's missing to get me to the x-axis. 60 is in my chart. So rather than doing the secant of 120, let's look up what the secant of 60 degrees is. And according to our chart, that's equal to 2. But remember, our final step is to determine what our sign is, S-I-G-N sign, whether we're positive or negative. So that's where these letters came into play. We were in quadrant 2 where sign would be positive, but anything else would be negative. We didn't do sine, we did cosine or secant. So this tells us I have to put a negative sign back on my answer. So the original problem, the secant of negative 240 degrees, is negative 2. Using my periodic properties this time didn't get me too much of a shortcut, but remember, it's just an option for something you can use. Okay, let's try tangent of 570. Recall that tangent had a separate period. It wasn't 360. The period of a tangent function is actually just 180. So you don't need to subtract 360. You can actually go by smaller increments. And it turns out I've done this one ahead of time, and it turns out that if I subtract 180 3 times, remember you can do it as many times as you want to, that's enough to get me down to an angle that's a little more convenient. I end up with 30 degrees when I subtract 183 times. And you can double check that for yourself. This time it is somewhat of a shortcut because tangent of 30 degrees is right there in the chart. This comes up to be the square root of 3 over 3. So this time it was a shortcut. I don't have to worry about signs because I got an angle that was in the chart. Let me show you how we can do the same thing using radians, although if you've got it, then this is not going to be anything new. Once again, I want to go ahead and use my periodic properties to make a smaller angle. I'm dealing with sine. The period of a sine graph is 360, or in radians, that's 2 pi. So what I need to do is, again, keep subtracting 2 pi until you get down to a more convenient angle. We've talked about this in the coterminal video, if you want to go back and watch it. What I'd recommend if you're using your calculator is I would type this in. Don't type the pi symbol in. Just type in 13 over 3 and subtract 2. And again, you can do that as many times as you want to get down to an angle that's a little more convenient to use. And it turns out that subtracting it twice gets you down to just 1/3, or just pi over 3. Again, it's a shortcut because I can look up the sine of pi over 3 in the chart, and I know that that's just the square root of 3 over 2. So I can find a coterminal angle with this original angle to make the problem a little bit easier to do. Okay, so same thing we did up above, just dealing with radians this time. Again, I'm dealing with an angle that's over 2 pi, so I'll subtract 2 pi a few times, and again, I've done this ahead of time, so I know it took me 2 times to subtract that. And if you're not sure how I'm getting these numbers, then pause and confirm on your calculator. Remember, if you're trying to do this by hand, I cannot just subtract 2 from the numerator. I need to find a common denominator and all that stuff. So I'm just using my calculator to make these a little bit easier to do. Once I subtract 2 pi twice, though, or 2 twice, I end up with 1 over 6, and if I throw that pi back on it, I get pi over 6. Okay, so I have found a coterminal angle, and again, this is more convenient to do than the original problem because cosine of pi over 6 is, again, in that chart that we've made. That's just square root of 3 over 2 again. Okay, and then we'll do one last example if you're not having fun with this yet. I want to do the cotangent of negative 9 pi over 4. And again, these are just options. You don't have to do the problems this way. It's just an option for you. Recall that cotangent and tangent have a different period. This time the period is just 1 pi. And I'll be adding it this time because my angle is negative. So again, I've worked ahead and I figured out that I had to add it 3 times. You can pause the video and try that for yourself. But if you take negative 9/4 and add 1 to it 3 times, you end up with cotangent of 3 pi over 4. So again, here's where it's not that great of a shortcut. 3 pi over 4 is not one of our special angles in that chart. So I still need to do the 3-step problem. So I'm going to go ahead and do that. If you've got the idea, you can stop the video now. But let me show you one more time how these 3-step problems work. So 3 pi over 4 is over here in quadrant 2. My reference angle is just pi over 4. We've talked about that in a few different videos. So I want to look up what the cotangent of pi over 4 is. And according to the chart, that's equal to 1. But remember, I have to determine, because I'm doing the 3-step problem, I got to figure out if that's a positive 1 or a negative 1, depending on what quadrant we're in. Since we ended up in the second quadrant where sine is positive, but anything else is negative, I didn't do sine, I did tangent, cotangent. So I need to throw a negative on that answer. So my final answer is going to be negative 1 for this. Okay, so again, that was how to use periodic properties to sometimes make the problems a little bit easier to do. Although it's an option. You definitely don't need to use periodic properties. You could have evaluated these using the original 3-step method on all of them. But as you saw, sometimes we can avoid that 3-step method.